Um, our next keynote from Professor Maria-Esther Vidal. Professor Vidal is a professor at the University of Hanover, where she leads the scientific data management group. And she has contributed to research in multiple areas, including the semantic web and distributed data management and distributed mediator-based query processing. She has published over 200 research papers, and they have been published in the top venues in databases, bioinformatics, AI, and data science, and also in the semantic web. Professor Vidal has received the German Science Award for Responsible Research and also the Leibniz Best Minds Program for women faculty. She has done a wonderful job mentoring many students, including about more than 30 PhD students and a couple of hundred master's students, and this in many countries, including in South America, Central America, and many countries in Europe. And I will also note that I am her advisor, actually, so I'm kind of the grandmother of all of these colleagues. And she also, her research is funded right now by many EU H2020 projects. So with that, I welcome Maria Esther to make a presentation.
Well, Luca, many thanks for this kind introduction. I wish you all a prosperous and peaceful new year. And well, many thanks for the invitation to present our work. As Luca says, I was her doctoral student, and today I will talk about challenges of knowledge graph and their applications in biomedicine. So, well, so I'm coming and affiliated with the Leibniz University of Hanover. So we here, and also with the Leibniz Information Center for Science and Technology. And this is a big library. This is one of the largest library in the world. And our aim here is to manage data that is coming from different data sources. So this couldn't be the best place for me to develop data management techniques. Just to motivate the work that we are doing in our group, just have this very simple example where we illustrate what the clinicians do when they have to prescribe a treatment. So usually they have to rely on clinical records in order to analyze in an integrated view a particular person, right? So they have images, clinical records, tests, and the results of different clinical analysis in order to be able to identify what is the disease that this person is suffering and propose an effective treatment. Happen to be that not only these clinicians need to analyze the clinical records, tests, and images, but also many times they have to go into clinical trials. They have to analyze the literature, and also they have to analyze the scientific databases. And all this is, if we think in terms of data management, there are many problems that are bringing big challenges. For example, heterogeneity. All these data, even they are human readable, they are heterogeneous. They are presented in different formats. For example, we have images, textual clinical notes, labs tests. In some cases, they are missing data, right? Because not all the results are together, or not all the tests are together. There are many cases, there are large volumes of data. So, for example, imagine they have to go back home, search for the literature, or they have to analyze different clinical trials, and not always the quality is good. Okay, so Our aim is not is to support these clinicians in order to provide not only human readable data but also machine readable data in the way that computers can support these clinicians in order to help them in the decision of best treatments, the diagnosis towards personalized medicine. And in order to do that, it's clear that there are many types of data sources that need to be processed, that need to be ingested, and then problems of data integration need to be solved in order to have knowledge discovery, to support hypothesis formulation. And in that case, this machine readable data that is transformed into what the clinicians are going to use need to be also transformed into knowledge. And this knowledge is the one that supports to support uncovering actionable insights. So, well, in my talk today, I'm going to talk first about knowledge graph in order to be all of us in the same page about what are knowledge graph, what is data integration, particularly in biomedicine, what are the pipelines for knowledge graph creation, and I'm going to talk about a neurosymbolic system that we are developing in the area of biomedicine, and of course, future directions. So let's start with knowledge graph. So what are knowledge graph? Knowledge graph are basically data structures where we are able to combine the convergence of knowledge and data and using a particular graph data model. Okay, so in this knowledge graph, so we have data, knowledge, and also the insights that can be inferred or can be discovered from this data and knowledge. And what is important is that entities and their relationships are fair class citizens. And together in this knowledge graph, we have metadata that describe the meaning of the data that is integrated. And on top of that, we have inference processes that are able to deduce new facts. So when we think in terms of a historical perspective of what are knowledge graph, we can go back almost 2,000 years ago, okay, when formal systems, logic, knowledge representation, and reasoning were the main topics that were studied. And there, when we think in terms of formal systems, that they were aiming to formalize the or emulate formal reasoning and provide visual representation of knowledge, there the concept of knowledge graph actually started to appear. So also when we think in terms of the initial work in AI, when we have formal representation of knowledge using logic, or when we have frames by Minsky or semantic networks, these are also knowledge graph or expert systems that actually are the ones that were not using data models, but also were aiming to formalize that. And when the description logic was defined as a logic to represent actually what we have currently in knowledge graph. But the initial point that we are considering, the starting point of what we are doing right now, is this a paper that was published in 2001 when Tim Berners-Lee, Hengler, and Oral Asila were presenting the semantic web as a new way to publish data, when we not only have data readable by humans, but also understandable by machines. And when I'm saying understandable by machines, I'm considering that not only the points, the relationships between the entities are understandable by these machines, but also the meaning of these uh, entities. Also, an important perspective that we have to take into account is that the semantic web or the have created a consortium where different standards have been defined. And these standards are standards that enable to model this knowledge graph. So there are data models that are standards, for example, the resource description framework or the OWL are formalisms that enable the representation of this knowledge graph. There are existing knowledge graphs that we will see later, and the importance of this knowledge graph, as for example, Jago, DBpedia, or Wikidata, that are encyclopedic knowledge graphs that actually are making available universal knowledge in the way that not only humans can understand and read that, but also machines are able to connect to this knowledge graph in order to extract contextual knowledge that is going to enrich the existing processes that we are implementing. In that way, our world right now is more in the way that we need to integrate data that is heterogeneous. We need to represent this data using graph in an efficient way, and we need to perform formal reasoning. And in the way that not only they are understandable by machines, but also they are able to be reused as contextual knowledge to enhance explainability and the validity. So all these papers are papers that actually I consider that they are very interesting and to this topic. So knowledge graph, we say, well, who is using knowledge graph? And we can see that knowledge graph are almost everywhere. So when we see in terms of the literature, the number of publications that have been published using or describing or proposing new approaches for knowledge graph is growing every year. And if we see public or private knowledge graph that have been available and the companies that are using them, more and more big companies and big organizations, as for example, the European Commission or Facebook or Google, they are relying on knowledge graph in order to keep their data. And this publication, I really recommend you to read that because it's presenting how knowledge graphs are actually contributing to industries in order to facilitate their work. So companies are Microsoft, they have their own knowledge graph, Google, Facebook, eBay, and IBM, and just to mention some of them, okay? So and in particular in TIB, in this big library in which we're part of, so we have what is called the Open Research Knowledge Graph. And the Open Research Knowledge Graph is a big knowledge graph where scientific publications are represented as fine-grained facts, where, for example, instead of having the publications readable only by humans, now the machines are also able to understand these publications and are able to establish connections between the publications in order to facilitate the analysis and the comparison between these publications. Or in my case, I'm developing this knowledge graph where we have lung cancer and cancer data that have been integrated, and this knowledge graph is putting together or integrating together cancer data, breast cancer, lung cancer, drugs, interactions between the drugs, and also publications in the way that we are able to support what is, for example, published or extracted from a particular clinical note. And in order to see what is available publicly, because many of these knowledge graphs or probably are private, we can see that also there is the link open data cloud. When see how many knowledge graphs are available, and not only available, are connected, and they are available and accessible via the web using interfaces as Sparkle. And in particular, I would like to highlight in life sciences. See how many knowledge graphs and how many triples are available here. And this link open data cloud that is a knowledge graph or knowledge graph. So see how they are, this knowledge graph has grown over the years and is growing and growing and growing. And when we are seeing in the life sciences, see that the part of the knowledge of the linked open data cloud, when we have data about the life science, see that each of these points actually is a knowledge graph that is connected to other knowledge graphs. And in here, I would like to capture your attention in two particular knowledge graphs. One is Wikidata, and the other one is DBpedia. Wikidata is like Wikipedia, but for structured data, where people are uploading knowledge, encyclopedic knowledge, as factual statements. And this is a collaborative platform or a collaborative knowledge base where anyone can publish knowledge. Of course, knowledge not like in Wikipedia, but structured knowledge. And of course, conflicting data may exist. And in that case, we are having a curation process that enables to improve the quality of this. When we think in terms of what type of data is stored in this big knowledge graph, we have many different type of data points, but in particular for life science, this is considered a knowledge graph for life sciences, where we have genes and proteins, genetic variants, chemical components, pathways, and diseases, and all of them connected. That is one of the most important things. So let's see an example of this. So we can go to Wikidata and we have our part that is human readable. But when we think in terms of machine readable, there are factual statements. So, for example, binaural bean is a drug that is used for treating a medical condition. In this case, some of the diseases that are treated by binaural bean are breast cancer, ovarian cancer, and non-small cell carcinoma. And this is not only facts that are existing in Wikidata, this is a very simple example, but also the statements that explain when this drug was approved, for example, for treating non-small lung cancer, and when that was approved. So, for example, this statement is saying that binaural bean is a drug that is used for treating the medical condition non-small lung cancer, and the date of the approval was in 1994 and is actually approved by the Food and Drug Administration. In terms of contextual knowledge, this is a very rich approach for representing not only statements, but also the context of these statements. So similarly, we have Wikipedia, but Wikipedia is just the representation of what exists already in Wikipedia. And actually, they are published following certain principles of LinkedIn. And it's also accessible via Sparkle endpoints and also linked to existing knowledge graph. And when we think in terms of, again, they have a large number of data types, but in terms of the life sciences, what we can see here is that we have biomolecular, chemical substance, and diseases, and it's also linked to the Wikipedia and to Wikidata. So when we see, for example, binaural bean, we have the textual description of what is the drug and many attributes that describe that particular drug. And the same with diseases, and the same with pathways, and the same with drugs, and many other concepts. And again, they represent a very rich machine readable representation of contextual knowledge. So let's when we have all this together, now what we have to think is how we can use all this in order to actually understand how we can make use of this knowledge graph for developing applications. So I will focus in knowledge integration and background knowledge to enhance the behavior of predictive models. So, but before thinking in how to use that, let's think how actually we can integrate this data. So just a very simple example. We have three data sources. I don't need to have even more than that. I have three data sources. And in these three data sources, first, I have structured data. Not necessarily this is the case. Probably we had to perform some pre-processing before. But here I have a relational database that keeps information about clinical records. So I have the person ID, I have the diagnosis, I have the treatment, which by the way doesn't have to be in the same language that, for example, the treatment is annotated or described. We have the doses that doesn't have to follow a particular format. We have the start date, the end date. And also we can have, for example, the family antecedents in terms of how this person had relative with cancer. And also we have scientific publications. As I said before, these scientific publications are human readable. And we can also have from scientific databases as drug bank semi-structured data that, for example, in this case, describe what are the results of interactions between two drugs. For example, this is a drug that it is described in terms of this test that says the combination of binaural being with cisplatin may increase the adverse effects, or metabolism of binaural being may be increased when combined with omeprazole, or the metabolism of omeprazole may be increased when combined with cisplatin. And all these sources are sources that are referring to drugs that are used in the treatments of these people. So it's important that the clinicians take first into account the results that have been published after conducting clinical trials with the use of these drugs, or the interactions that have been reported that may exist when these drugs are combined. So the problem of that integration, we all know that is a very challenging problem that needs to collect data from different data sources and merge them in the way that we can have a unified view of that. So when we think in terms of what is this unified view, there are control vocabularies. As for example, UMLS. UMLS is the Unified Medical Language System that provides a control vocabulary and contextual knowledge to align biomedical concepts present in biomedical data sources. So, for example, here, see that I have term that in this case is non-small lung cancer. So the same term, non-small lung cancer, we have different definitions provided by the different providers. But what is important is that these definitions and these labels are providing contextual knowledge, which is extremely important for determining the concept that we are defining. Not only these concepts are described based on labels and definitions, but also they have semantic types for which also there are labels and definitions, and also semantic groups. When we think in terms of how this can be used in order to annotate all these data sources that even they are talking about the same concepts. The humans can understand that, but the machines are not able to understand that. Our aim is to annotate these data sources with these control vocabularies. And for doing that is what is called the problem of name entity recognition and linking is there, okay? And in my group, we have developed a tool that is called Falcon, and this tool is able to map software form within short tests into entities and relationships in a knowledge graph. And this knowledge graph can be Wikipedia, Wikidata, DBpedia, or UMLF, or any other knowledge graph. In the way that when we see the short test is seen as set of tokens. So in this case, T1, T2, up to M, and a set of entities and relationship from the knowledge graph. And the idea of these techniques of entity name, entity recognition, or linking is to identify which of these group of tokens can be linked to a particular entity in this knowledge graph. So in that case, we are maximizing the number of tokens that are put together and linked to a particular entity, and of course, minimizing the number of entities. What happens is that these tools are guided by a set of rules based on English morphology and tokenization and compounding. And you will say, well, how this is linked or related to existing knowledge graph? Is that in that case, the knowledge graph provides the background knowledge that is used in order to first identify what is an entity. So, for example, we have this test, and in this test that describe a particular lung cancer drug, and this all this background knowledge that is provided by Wikidata, DBpedia, or UMLS is used to identify the entities and to link these entities to resources that are in this background knowledge. Okay, so when we think in terms of how this is defined, so I have a rule-based system that is built on top of background knowledge and is implemented as a deductive database. And this deductive database, it has a set of rules. So a set of rules, first a set of linguistic rules that describe where are these concepts. So for example, verbs are not entities. A single compound word comprises words without stop words, or an entity includes entities with at most one stop word. So we have linguistic rules that are actually enabling to decompose or tokenize the initial test, and then we are able to also using domain specific rules, again implemented as a deductive database, that are using the providing the basics to recognize the candidate entities. And then a background knowledge that is integrating all what is part of this knowledge graph. So for example, we have the resource or the entities, the label, the language, the provider, the confidence score, the definition of that concept, and the equivalences, the same as the synonyms between all these concepts. And this is actually what is helping to identify the candidate entities. And actually, as I said before, the entities are defined in terms of labels, description, and semantic types, and the same as relationship that corresponds to the equivalent, the logical equivalence, is used to deduce, to infer new equivalent resources. So when you think in terms of how this works and how well this approach is, we have extensively evaluated these approaches in existing benchmarks in the task of name entity linking and name predicate linking. And these are the state of art approaches in a state of the art benchmark. And as you see, Falcon, just by implementing these rule based approaches, is able to outperform existing approaches just using this rule based approach. Okay. But when we go into biomedicine, biomedicine is more complicated domain. When we have, for example, the med mentioned data set that comprises all these many abstract and publications from PubMed and all these many UMLS concepts, we see that our approach, when it's compared to Science Spicy or other approaches, is actually competitive, just considering the rules and without any background knowledge. So when we saw that, we said, oh, but we can do better. And we can do better because from this side, we are just considering symbolic knowledge. We are considering just what we have in the knowledge graph and deductive databases. But why we don't make a neurosymbolic approach that actually is able to exploit all what we know from the symbolic world and what we can have when we have embeddings, when we have sub-symbolic representation of knowledge. So saying that, we have developed a combined, a hybrid approach where we have symbolic and sub-symbolic knowledge. And as we did before, we are able to generate a set of candidates. But then we make use of sub-symbolic system that is able to have contextual knowledge encoded in embeddings. And the contextual knowledge is actually what is represented with the labels, the descriptions, and the definitions of these concepts that, as you saw before, we have it in DBpedia, we have it in Wikidata, and also we have it in UMLS. And this is the contextual knowledge that is used to have these embeddings, but at the end are used to have limb prediction. The limb prediction of the types of these entities that are identified by the symbolic system. And this is what is used to disambiguate, because at the end is what is used to predict what is the type of these entities and actually have better, improve the quality of the prediction that we have. So saying that, when we go back to our experiment where we have the med mentioned data set, now we can see that we are using a trained bird in order to have this in the biomedical domain, and this is pre-trained by 10 epochs, and we have false samples are generated by replacing correct semantic types with wrong types. And actually, at the end, what we are having is negative samplings that are even, they are same UMLS, they are not in the branches of the types that we were having initially. And see what is very interesting here, that we started with a system that was competitive with respect to the existing state-of-the-art approaches. When we do have only pure symbolic approaches, we are not as good as the previous one, but when we combine both, we are able to outperform basically what is in the state of the art. So with this is showing the importance of first using what is encoded in the knowledge graph, say that the Wikidata, UMLS, or DBpedia, and then going to embeddings, going to sub-symbolic approaches in order to actually exploit the contextual knowledge. So with this, we have the way to align all what you have in these different data sources, say clinical records, publications, or scientific databases. But you say, well, how you put everything together in order to have a knowledge graph? So this is what we call a data integration system. A data integration system is a triple where we are able to define the ontology, the sources, and the mappings. And actually, these mappings are rules that are defining the concepts in the ontology in terms of what we have in the data sources. And there are languages that are actually standards to propose that, in the way that we have the ontology, the data sources, and these mappings are able to, when they are executed, are able to generate this knowledge graph that comprises, the knowledge graph comprises the instances of these classes and the properties, and at the end are able to provide the unified view. And the quality of these are analyzed or validated using integrity constraints. And also we are able to have graph patterns that are enabling us to retrieve data. And you will say how these mappings are defined. And actually these mappings are defined with standards. So this is one of the standards that is used to define the mapping. So for example, we have a logical source that defines a concept, a class, C1, by using, and the instances of these classes are defined in this way. We have the predicates, we have a way to link these mappings. And when we think in terms of these data integration systems that I defined before, we just have whole clauses where we have the body and the head, and we have a way to define classes, the instances of the classes, using concept mapping assertions, rule role mapping assertions that define relationships or role mapping assertions that define attributes. Again, this is a declarative language that at the end is defined based on the physical operators. And the physical operators are just logical operators from logic, from the relational algebra. And if we remember, these operators can be physically implemented using different physical operators. And but at the end, the complexity of these are p space, which we also need to manage. And what we have is the MR Devicer, which is a tool that actually is able, as in query processing, to identify plans for the execution of these mappings, and for these plans, find also physical operators in order to execute these mappings in the most efficient way. And the most efficient way means that we need to reduce execution time, and also we need to reduce the amount of memory consumed in order to generate this huge knowledge graph. So saying that, when we compare, these are also experiments where we compare the performance of our approach, the SDMR Devicer, with different versions of the RDificer, and also existing tools as ARML, Mapper, and Rocket RML. And as you can see in the plots, we have different configurations of different sizes, and you can see that always planning, as in query processing, and having the physical operators actually improve the performance of the process of knowledge creation. And this is not only when we are considering a particular size of the data sources. This is observed in many different configurations. So as we add more data, also the improvement of these approaches also is observed. And finally, when we think in terms of integrity constraints, there is another standard that is called SHACAL. And SHACAL is a shape constraint language that enables to represent integrity constraints, as for example, lung cancer protocols that in this case indicate when these two drugs need to be administered. So for example, afatinib cannot be, is not recommended for non-small lung cancer patients that are negative for EGFR. But lapanibit is recommended for patients that are HER2 positive or EGFR positive. And happen to be that this language is a formalism that is in general MP hard. Validating these integrity constraints is MP hard, but they are tractable frameworks, fragments of SHACAL. And the tractable fragments are actually restricting the expressiveness, but in practice they are very useful. And we have used them to create our tool that is called TrashShackle. This TrashShackle approach has been published in 2021 in the web conference. And basically, we are following always the same idea. We have the first step when we plan the execution of these, in this case, integrity constraints. And in the second step is when we execute. But since these integrity constraints can be very expensive to execute, first we find a good plan, a plan that means an order of these executions of the integrity constraints, and then we have an interleaf execution of these integrity constraints, because these integrity constraints are mapped into a database. And the interleaf execution enables us to rewrite the request over the knowledge graph that need to be executed in order to collect the data that is going to be validated. What is good with this approach is that this interleaf of the execution of these queries and the validation is enabling a trap shackle to identify invalid entities very fast. And this also is helping TrashShackle to produce results incrementally and actually outperform state of the art by just reducing the number of integrity constraints that need to be validated. Because if we are able to identify that an entity just invalidate one constraint, we don't need to check the rest. So when we see how this performs, see that all this is reported in this paper. See here we are reporting the continuous behavior using the metric called DFT, and this DFT is measuring how good is the tool by producing continuous results, in this case, invalidated or validated entities. We have time for the first answer, execution time, the number of entities that are produced. And here we are comparing all the existing approaches. So our approach that is called Shackle, and also the state-of-the-art approaches that are called Shackle to Sparkle. And these are higher error matrices, so that means that the higher values are the best. And see what happened, that by using this approach that is able to first order plan the execution of the validation, second produce the interleave of the validation and the collection of the data, and produce results incrementally, we are able to outperform the state of the art. And why? Because first, the state of the art will need to validate these many constraints, while here, by doing this, we are able to reduce the execution of this integrity constraint, because we are able to produce the results and invalid entities very fast. We are able to identify these very fast. And see that this is not in many different knowledge graph that we have validated. And of course, when the knowledge graph is more or low quality, we are performing better, because more that they are invalid entities, the faster that our approach is able to perform. And see that there are settings where we are able to reduce in several orders of magnitude the number of rules that need to be validated. And of course, that enables Shackle to generate answers very fast, finish the execution of this faster, and also scale up to large data sources. But this is in terms of, okay, what we can do at the level of generating this knowledge graph. But let's see how this is applied. And for applying this, we have this neurosymbolic approach that has been applied in all these projects that Rika was mentioning before. And what we wanted here was to have an approach that was able to have the semantic data modeling and combine the good thing of what we saw before of the symbolic systems with the neurosymbolic approaches. So we have our knowledge graph, we have treatments. So, for example, we have a person, we have the treatments that this person has received, the drugs, oncological and non-oncological, the definitions of these drugs. And at the end, we want to solve the problem of predicting the response of these treatments, okay? And for predicting the response of this treatment, we see this as a hybrid approach, a hybrid problem. When on one side we need to deduce what are the interactions that exist in a particular treatment, and once we have deduced the interactions that exist in a particular treatment, we use embeddings, we use symbolic representation of this knowledge graph in order to solve the problem of link prediction. And the problem of link prediction in this particular case is to predict the effectiveness of a particular treatment. So saying that, we define our neurosymbolic system with a knowledge graph. So we have first the knowledge graph, as we say, with this is a directed label graph, where we have a predictive property that is not going to be predicted, a predictive problem. In this case, we are predicting the tail of the triples, and we have a data integration system that has, in this case, a deductive database, where we have the extensional database are the ground facts in the knowledge graph. In this particular case, the ground facts for the head and the tail of the predictive problem. And the intentional database are word clauses that define new relationships between the ego networks of the head and the tail of the predictive problem. And of course, we have a the neurosymbolic approach. The subsymbolic part is defined based on a embedding model that is defined based on a scoring function that estimates the plausibility of a vector representation of a particular triple that is the one that is inferred. And the lead prediction task is the process of finding this tail, in this case T, that is the best scoring tail for each of the triples that we have, that we are predicting. And of course, we are maximizing the values of that scoring function. So, saying that, now our deductive system is a deductive system that defines the drug-drug interactions that exist in a particular treatment, and the embeddings are defining these drug predictions. So just to give you an example of this deductive system. So pharmacokinetic drug-drug interactions are are interactions that exist in a clinical in between two drugs, and they are affecting the absorption, the distribution, the metabolism, or the excretion of another drug. So, for example, in this case, we have that on that zone can decrease the metabolism, can be decreased the metabolism when it's combined with omeprazole, and also that etoposide can be, the metabolism of etoposide can be decreased when it's combined with ondansetron. But see, when we have a treatment that actually combines these drugs, there is a new interaction that is not reported that exists. Why? Because these drugs are put together, and this is what is deduced. And this is what our system define rules that is able to infer all this. When we think in terms of embeddings, we need to combine several embeddings, not only we have different embeddings, okay? And at the end, what we have the treatments with the dues interactions with the ones that we have, and we have the dues system that actually have the interactions that are extracted from drug bank using Python, and the dues that are have with this drug-drug interaction in inductive system, and we have the embeddings, okay? And basically what we have is that we have built a big knowledge graph, and this big knowledge graph is composed of clinical records that are for lung cancer patients. We have drugs, we have oncologic, non-oncological drugs, we have surgeries, we have publications, and the publications are used to extract interactions. And we have also interactions between drugs that have been extracted from drug bank. And when we have this deduce system, we see that we are able to have the symbolic and the subsymbolic approach. The subsymbolic approach is implemented by Viking, and this is with these standard configurations. And what we can see here is that we have, just to evaluate and show you what is the effect of having this symbolic system, we have three knowledge graphs. The one when we only have everything integrated, the one when we have the deduced interactions between the drugs in a treatment using our deductive database, and the knowledge graph G3 that includes the original data plus all these interactions are random interactions, are not interactions that actually are deduced by our deduce system. And what we can observe first is that definitely treatments that are effective usually do not have as many drugs as the ones that are low effective. But what is important also is the number of drugs, interactions between drugs that are reduced, that we can see that actually the treatments that are low effective, they have more interactions that can be reduced. So definitely these treatments that are seems to be low effective seems to have more interactions in the drugs that are administered. Also, they have more drugs. So, but see the result of the comparison of all these knowledge graph embedding models. So my aim is not to compare the actually the performance between embeddings, but compare the improvement on the performance of embedding when we have this symbolic approach. And see that G2, remember G2 is the symbolic approach. Is the knowledge graph that includes the results of the deductive system, and see that always improve the first one, that is the original graph, but also is much better than G3. And G3 is the one that includes the original data, but we have connections that are randomly added. And this is shown not only in precision, recall, but also in F measure. So if consistently we are able to improve the performance of these embeddings when we are actually adding more contextual knowledge. And this is observed not only with uniform negative sampling, but also when we use other type of sampling. So for example, Bernoulli sampling. And why this is happening, just showing you, I want to show you an example. So these are 5 treatments that are incorrectly classified in the knowledge graph G1. And why? Because, of course, this contextual knowledge is not given the model, the knowledge graph embedding model, the capacity to position these vectors in the correct position in the space. And this is observed here. So G2, remember, is a knowledge graph where we have all these deduced drug-drug interactions that are enhancing the context of these treatments, and see that when we find the distance or the similarity measure between these treatments and similar treatments, so that means treatments that are actually low effect and have similar drugs, the similarity in all the cases is increased in G2. So this positioning that now the embedding is able to have, because the context have been enhanced with what we have collected from the knowledge graph, is actually empowering the knowledge graph embedded models to have better position, better predictions, and also to position better the embeddings in the space. So, well, saying that, well, these are definitely results that are telling us that knowledge graphs are promising data structures to represent knowledge, but there are many things that need to be solved. So, first of all, see this example. This is a guideline that need to be followed in order to prescribe treatments, for example, in breast cancer. So we have the person is depending on the stage of the person, a particular treatment is prescribed, and also depending on the biomarkers that the person have, the neoadjuvant treatment can be prescribed or not, and also depending on the biomarkers, we need to prescribe a new treatment. We have to follow a workflow. And what happened to be that none of existing approaches is able to naturally represent these approaches or these situations and evaluate in an efficient way them. So one of the problems is to provide languages able to specify that. Also, it's important for the clinicians to be able to validate the results. So, for example, we have entities in the knowledge graph that invalidate a protocol. So when invalidate a protocol, is an invalidation of the protocol because was an error of us or actually was an error of the data. So we need to be able to query, to annotate the data with the whole trace, how data was integrated, how data was collected, how data was cleaned, and having all this metadata and being able to query this metadata. So query processing need to be changed in order not only to have retrieved the answers, but also to annotate these answers with the metadata that indicates how data was collected, how data was integrated, and how data was validated. And finally, causation is extremely important. And I haven't mentioned anything about causation, but in biomedical domain, causal relationships are very important, and happen to be that existing approaches do not consider the relationship that may exist in knowledge graph when we have subclasses, we have relationships, we have cardinality, integrity constraints. And these new approaches need to be defined in order to enhance our predictive models, also enhance our inference processes. And finally, as I was showing at the beginning, when we have knowledge graph that we are integrating, as for example, Wikipedia, DBpedia, Wikidata, UMLS, we have multimodal knowledge. And for here, I can show you that we have textual material, we have images, we have formulas, we have a provenance, and happen to be that existing approaches are not able to put together all these multimodal values of data in order to create embeddings that are actually more expressive. And this is also another approach that need to be another problem that need to be taken into account. So saying that, what are the summary of this? That well, actually, there are many challenges that need to be addressed when we are thinking in this pipeline that the clinician need to follow in order to prescribe or a treatment or have a precise diagnosis. And definitely, the approaches that we are describing today are promising, but there are many things that need to be done, right? It's not that just having this knowledge graph is enough, that we need to have on top of that powerful neurosymbolic systems that are able to put together different contextual knowledge represented in heterogeneous data sources and heterogeneous knowledge graph in order to be able to have precise predictions. And is that in where we are going to work with the federated multimodal neurosymbolic systems. And well, uh, all our tools are publicly available. This is my group. This is a huge group where we are actually trying to develop all these things. And well, many thanks for the opportunity to present our work here. So thank you.
Thank you very much. And we have 2 minutes for questions. We have a lot of questions. So,
Thank you, ma'am, for the presentation. I have two questions actually. First, in a Falcon, there's a slide in which the numbers of entities were tried to be reduced. So I just want to ask if the entities are reduced, is there any loss in information? Because we try to go for more fine-grained entity to get more information. And there's a example also you've given that in drug-drug interaction, there's a 1 million entities.
sure, we have.
So why reduction was done? And my second question is that um, why F1 score was not considered, but accuracy was considered while calculating the entity linking in Falcon to UMLS. So these two questions.
Okay, so let me go to the slides of Falcon. Sorry, I don't know how to move well here. Let me go to Falcon. Okay, let's see how I can. Okay, so in Falcon, why we are minimizing the entities. Actually, what we want is to be able to group together several tokens in a particular entity. So what we want is to be able to say that if, for example, you have non-small cell lung cancer, actually, if you don't want to minimize the number of entities, you could also have cancer as one element. You can have lung cancer as another. So lung cancer and also non-small cell as another resource. But what we want is to be able to actually put together several of these tokens and minimize what we are identifying as entities. So the entities are the resources in the knowledge graph that we want to be able to have a resource that is the most specific one that represents the several tokens that are identified. So that's why we are saying that we are maximizing the tokens that are put together in order to link them. So that's why it's not that we are just identifying tokens, it's that we are identifying the maximum number of tokens that can be linked to a particular entity. And this ends up maximizing the size of the tokens, the number of tokens in the entity that we are identifying, and at the end, minimizing actually the number of resources that the end we have. Okay, so this is what we are talking. We are saying here in Falcon. The other question that you have is in order here. Sorry, could you repeat that in the evaluation of Falcon?
Yeah, let's have your question.
Yeah, so in Falcon, you have used entity linking and NER to get new to expand the knowledge graph. So
Mhm.
so you are using existing entities in the knowledge graph, and you are linking it to mentions in the text. So are you looking at relations that are present in the text also, like
Yeah,
two
yeah,
entities, two
yeah.
mentions within the text and relation?
Actually, if you see these results, you see my screen, right? We are Falcon is recognizing entities and also recognizing predicates, recognizing relationships. So we are actually solving both problems. Yes, and see these are these are the results of benchmarks. These are for entity linking, while this is for predicate linking. Yeah, yeah, yeah.
Thank you.
And Falcon is publicly available. So we have that. You can download, you can use the API. So even for linking to DBpedia and Wikidata, but also for linking to UMLS.
Thank you.
You have another question regarding the prediction of link prediction.
I think the question was why you used an F1 score for a prediction.
Actually, this is part of one of the results. We also have many other matrices that I didn't have time to report, but this is just to show the performance. But in the papers, definitely there are many other matrices that we are reporting in this particular problem and also in the problem of link prediction, where we are reporting hits at K or MMR.
Thank you very much. Thank you, Maria Esther.
Well, many thanks for the invitation.